Introduction to Collinearity. Welcome, everyone. Today we are going to explore a very important concept in coordinate geometry, determining the collinearity of points. To start off, let's look at the terminology. The word collinear might sound a bit complex, but it's actually quite intuitive if you break it down. It is derived from the prefix co, which means together, and the word linear, which refers to a line. So, when we talk about points being collinear, we are simply talking about them being together on a line. More formally, we say that three or more points are collinear if they all lie along a single, straight line. Now, here is a helpful way to visualize this. Imagine you have 3 points, let's call them A, B, and see if these points are not collinear, meaning they don't sit on that same straight path. They will naturally spread out and form the vertices of a triangle. Because of this, you can think of the test for collinearity as a way of checking if these points fail to form a triangle. As we move through the next few slides, I will show you the mathematical principle we use to prove whether these points stay on a line or break away to form a triangle. The mathematical principle. The fundamental concept we use to determine if points are collinear is based entirely on the property of distances. Think about the geometry of a straight path. In any straight line, the shortest possible distance between 2 points is always the direct line segment connecting them. This leads us to a very specific rule. If we have 3 points, A, B, and C, and point B lies directly between points A and C on that straight line, then the distance from A to B, plus the distance from B to C, must be exactly equal to the total distance from A to C. If there is even a slight deviation, the distances won't add up perfectly. We will use this exact logic in the next slide to establish our formal mathematical condition. Now that we understand the definition of collinearity from our previous slide, that these points must all lie on a single, straight line, let's look at the mathematical principle that actually allows us to prove it. The condition for collinearity. Now that we understand the basic principle of distances on a straight line from the previous slide, let's look at the specific mathematical condition we need to satisfy to prove collinearity. 3 points, A, B, and C, are considered collinear if, and only if, the sum of the lengths of any 2 segments is exactly equal to the length of the third segment. To be mathematically precise, we have to account for the fact that we might not know which point lies in the middle. So we express this in 3 possible scenarios. First, if point B is positioned between A and C, then the distance from A to B plus the distance from B to C must equal the distance from A to C second. If point A is the middle point, then the distance from A to B plus the distance from A to C must equal the distance from B to C, or third, if point C is the middle point, then the distance from B to C plus the distance from A to C must equal the distance from A to B. However, it is equally important to recognize the alternative. If the sum of any 2 distances is strictly greater than the third distance, for example, if A to B plus B to C is greater than A to C, then the points are noncollinear. In this case, the points won't lie on a single line, but will instead form the vertices of a triangle. We will see how to apply this logic in our upcoming worked example. Real-world analogy. Now, to help you visualize the mathematical principle we just discussed regarding distances, let's step away from the coordinate plane for a moment and look at a real-world analogy. Imagine you are planning a road trip between 3 different cities. Let's call them City A, City B, and City C, and these cities are all located along a perfectly straight highway. If you decide to drive from City A to City B, and then continue from City B to City C, your total distance traveled will be exactly the same as if you had simply driven directly from City A to City C without any stops. This perfectly illustrates the condition where the sum of the 2 smaller segments equals the total length. However, consider what happens if City B is not on that straight highway, but is instead located somewhere off to the side. In this case, you would have to deviate from your straight path to reach City B, which would inevitably make your total journey, that is, the distance from A to B plus the distance from B to C, longer than the direct route from A to C. This deviation is exactly what happens when points are noncollinear. And as we will see in the next slide, this is the fundamental logic we use to determine if points form a triangle or a straight line. Step-by-step procedure to verify collinearity. Now that we understand the theory and the real-world analogy of how distances behave on a straight line, let's move on to the practical application. I'm going to walk you through a clear, 5-step procedure that you can follow every single time you are asked to verify collinearity. Step 1. Your first task is to calculate the distance between points A and B. To do this, you will apply the distance formula, which is the square root of the quantity x sub 2 minus x sub 1 squared plus the quantity y sub 2 minus y sub 1 squared. Step 2. Next, you need to find the distance between points B and C. You'll use the same distance formula, but this time, you'll use the coordinates for the second and third points. That is, the square root of the quantity x sub 3 minus x sub 2 squared plus the quantity y sub 3 minus y sub 2 squared. Step 3. Don't stop there. You must also calculate the distance between points A and C again. Using the distance formula, you'll find the square root of the quantity x sub 3 minus x sub 1 squared plus the quantity y sub 3 minus y sub 1 squared. Step 4. Once you have these three numerical values, look at them closely and identify the longest segment. You are looking for whichever of the three calculated distances is the largest. Finally, step 5. This is the moment of truth where you check the sum. Take the two shorter distances you calculated and add them together. If their sum is exactly equal to the longest distance, then you have proven that the points are collinear. If the sum is greater than the longest distance, then the points are not on a line, but instead form a triangle. We will put this exact procedure into practice in the next slide with a worked example. Worked example. Now that we have understood the theory and the step-by-step procedure, let's put everything into practice with a worked example. Here is our problem. We need to determine whether the 3 points, A with coordinates 1, 1, B with coordinates 2, 2, and C with coordinates 3, 3 are collinear. To do this, we need to follow the procedure I mentioned in the previous slide and calculate the lengths of all 3 possible segments. Step 1. Let's find the distance between point A and point B using the distance formula. We take the square root of the quantity 2 minus 1 squared plus 2 minus 1 squared. This simplifies to the square root of 1 squared plus 1 squared, which gives us the square root of 2 units. Step 2. Next, let's find the distance between point B and point C. Applying the same formula, we have the square root of the quantity 3 minus 2 squared plus 3 minus 2 squared. Again, this simplifies to the square root of 1 squared plus 1 squared, resulting in the square root of 2 units. Step 3. Now we must find the distance between the two outer points, A and C. We calculate the square root of the quantity 3 minus 1 squared plus 3 minus 1 squared. This gives us the square root of 2 squared plus 2 squared, which is the square root of 4 plus 4, or the square root of 8. Now, as I'll remind you in the next slide, it is crucial to simplify your radicals. The square root of 8 simplifies to 2 times the square root of 2 units. Step 4. Now comes the most important part, verifying the collinearity condition. We look at our 3 calculated distances. AB is the square root of 2, BC is the square root of 2, and AC is 2 times the square root of 2. By identifying the longest segment, we see that AC is the longest. Now, we check if the sum of the 2 shorter segments equals this longest segment. We add the square root of 2 to the square root of 2, and we see that it exactly equals 2 times the square root of 2. In conclusion, because the sum of the distances AB and BC is exactly equal to the distance AC, we have proven that points A, B, and C are indeed collinear. Before we move on to the final takeaways, let's look at some common pitfalls to avoid during these calculations. Common mistakes to avoid. Now, before we wrap up our lesson with the final summary, I want to pause and discuss some common pitfalls. Even if you understand the concept of collinearity, it is very easy to lose marks due to small, avoidable errors. Let's look at 3 specific mistakes you should watch out for. First, be careful about assuming the order of your points. It is tempting to just assume that point A, then B, then C are in a straight line in that specific order. However, the problem might give them to you in any sequence. To avoid this, always calculate all three distances first. This allows you to identify which segment is actually the longest and which point is truly the middle point. Second, pay close attention to how you simplify radicals or square roots. In our worked example, we saw that square root of 8 simplifies to 2, square root of 2. You must simplify these terms before you try to add them together. A very common mistake is thinking that square root of 2 plus square root of 2 equals the square root of 4. That is incorrect. Remember, you can only add radicals if the numbers under the root are the same, and even then, you are adding the coefficients, not the radicands. Finally, watch out for calculation errors during subtraction, especially when dealing with negative coordinates. This is a classic trap. If you are subtracting a negative value, remember that subtracting a negative is the same as adding a positive. For instance, if your x2 minus x1 involves a negative x1, it becomes x2 plus the absolute value of x1. One small sign error here will throw off your entire distance calculation. Keep these tips in mind, and you'll be much more accurate in your upcoming assessments. Now, let's move to our final slide to recap the key takeaways. Key takeaways. First, let's revisit the definition. Remember, the term collinear literally means together in a line. So, when we talk about collinear points, we are simply referring to points that lie on the exact same straight line. Next, let's summarize the mathematical test we've learned. To prove points are collinear, you must check if the sum of the two shorter distances is exactly equal to the longest distance. If they balance out perfectly, you have a straight line. On the flip side, we must remember the concept of the triangle inequality. If the sum of the two shorter segments, such as a B plus BC, is strictly greater than the third segment, a C, then the points are non-collinear. In this case, the points are spread out enough to form the vertices of a triangle. Finally, a very important procedural requirement to keep in mind for your exams. To properly check for collinearity, you cannot skip any steps. You must apply the distance formula 3 separate times to find the lengths of all possible segments between the 3 points. This ensures you have identified the longest segment and can accurately perform your final check. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear in your mind. That concludes our lesson on determining collinearity. Keep practicing these steps, and I will see you in the next session.